Hello everyone. Today we are going to work on section 11.3. We're going to look at perimeter and area of similar figures. Now remember, we've already looked and talked about similar figures, and remember that when we say two figures are similar, that means all the corresponding angles are congruent and their corresponding sides are proportional, which means when you write the ratio of the sides, like this side right here, side 3, let's try to get a better color here. So when we look at 3 to 6, the ratio of those sides, and 5 to 10, of course the other sides are the same, so that ratio will be the same. We can see 3 to 6 is equal to 5 to 10 because, of course, that also equals 1/2. So we've already talked about that, and I think we've actually already talked about their perimeters, but let's just take a look quickly at their perimeters. So if we look at the perimeter of triangle A, we can see it's 5 plus 5, which is 10, plus 3 more is 13. So the ratio of their perimeters is 13, 2, and then the perimeter of the other one is 26. And if we reduce that, we can see that the ratio of the perimeters is the same as the ratio of the sides. And actually, when we have similar figures, all flat lengths will be in the same ratio as the sides. In other words, when we look at the ratio of heights, for example, of these triangles, 4 to 8, that's also in the same ratio as their sides and same ratio as their perimeters. But we haven't really discussed, I don't believe, what about their areas. Well, if we find the area of A, it's 1/2 the base, which is 3, times the height, which is 4, or 1/2 of 12. And so 1/2 of 12 is 6. And then we look at figure or triangle B, and we have 1/2 of 6 times 8, or 1/2 of 48, which is 24. But when we reduce that fraction, that becomes 1/4. So they're not the same. The ratio of the sides and the ratio of the perimeters are the same, but the ratio of areas are not. But there is a relationship. You might not see it yet, but let's take a look at another example. So here, these rectangles are also similar. So if we write the ratio of the sides is 4 to 12, which is also 6 to 18, which is also the ratio of 1 to 3. So when we look at the ratio of and of course they're rectangles, so the other sides are the same. The ratio of the perimeters, you would have 6 and 4 is 10, and then you double that, so you would get 20 over, and then 18 and 12 is 10, 20, that's 30. No, that's 10, 20, 30. Oh, I have to double that, sorry. Yeah, it is 30, but then I have to account for the other two sides. So that is 60. So then we also get the ratio of 1 to 3. What about their areas? Well, the area of the first rectangle, 6 times 4, we get 24. And the area of the other one, 12 times 18, is, I'm going to grab my calculator here. You guys have probably already calculated it, but 12 times 18 is 216. Okay, well, we have to reduce that. I know that I could at least divide by 2 and keep cutting it in half, but I'm going to see if 24 goes into 216, and it does 9 times. So that reduces to 1/9. So now we can see again that they're not the same. But what you could start to notice is that if we were to take and square each of these, we end up with the ratio of the area. And so, of course, if we were in class, we would probably do some activities to kind of explore this on our own, but this is what happens in similar polygons. If two polygons are similar and the lengths of the corresponding sides have the ratio of A to B, then the ratio of their areas is A squared to B squared. So A to B for areas becomes A squared to B squared. And perimeter and any flat length, like a height, like a radius, like a diagonal, they will all have the same ratio of sides, A to B, but areas will be A squared to B squared. And when we get to chapter 12, when we talk about volume, you'll see that the ratio of volumes end up to be a cubed to b cubed because we're talking about three-dimensional area versus two-dimensional here. So let's try some problems and let's practice how to use these ideas. So it says these rectangles are similar. Find the area of the larger one. Well, we know the ratio of the sides is 4 to 12, which we always reduce that. So that would be 1 to 3. So that means the ratio of the areas is going to be 1 cubed to 3 cubed, or 1 to 9. So this is the ratio we're going to need to use because we know the area of this one is 37, so we need to find the area of this one. So we're going to set up a proportion because we know the areas have to be in the ratio of 1 to 9. So the 1 corresponds to the smaller one, the 9 corresponds to the larger rectangle, so that 1 to 9 area ratio will be the same ratio as 37 over some number. So now I can cross multiply and I get x is equal to 333 units squared. Okay, so now we found that missing area. And we didn't even need to know the other side length over here to find that area. And that's why this is so powerful, knowing this, because we don't have to have as much information. So now let's look at using this in a slightly different way. Look at these two similar polygons. Now we're given the ratio of the areas. So the ratio of the areas is 18 to 50. Okay, so again, I'm going to have to reduce that fraction, and I can first cut it in half, or I can notice maybe a larger number goes into each, but if I just cut it in half, this would be 9 and 25. And actually that is simplest ratio. So the ratio of the areas here is 9 over 25. So that means the ratio of the sides, okay, is going to be the square root of 9, or 3 over 5. So again, the ratio of the sides is always a over b. The ratio of the areas is always a squared to b squared. So we either have to square it if we have the side ratio, we have to square it to get to the areas. If we have the area ratio, reduce it, and then we take the square root. So now we'll set up a proportion. We want to find this other side. Well, this we don't even have to set up because we know this has to be 3 to 5. So we found the other side, but otherwise we would set up a proportion that the side ratio of 3 to 5 has to be the same as this side right here, 3, compared to the other side, which we don't know, but of course that's obvious. So hopefully this is starting to make sense. I would encourage you to read the textbook and look through some additional examples for more information. Okay, so let's look at this question. Now we don't have pictures, but we can certainly draw pictures. It says a larger baking pan is 15 inches. Oh boy, if we had to bake something 15 feet long. Okay, a larger baking pan is 15 inches long and 10 inches wide. A smaller pan is similar to the larger pan. The area of the small pan is 96 inches squared. What are the dimensions of the smaller pan? So again, it's always helpful to just sketch a diagram. It tells us that this larger pan is 15 inches by 10 inches. So we know the area here because we just multiply 10 times 15. So we get 150 inches squared. Okay, so now we look at the smaller pan. We don't know what the dimensions are, but we know that the area is 96 inches squared. So again, we start with, in this case, we have the area ratio is 150 over 96. Again, reduce, keep cutting in half. This would be 25 over 16, okay, if we keep reducing. And again, a fast way to reduce on your calculator is just divide 150 divided by 96 and then go to your math and change it back to a fraction button. That'll be the simplest. So now our area ratio has kind of got cut off here on the side, so let me write it a little bit more clearly. The area ratio is 25 over 16. So that means the sides are going to be in the ratio of 5 to 4. So now if I know this side right here is 15, then I want to find this side right here. So what I know is that that side ratio of 5 to 4 is the same proportion or ratio as 15 over x. So then I get 5x is equal to 60. So then x is equal to 12. So this side here is 12 inches. And then I just set up the same proportion to find the other side. So I would have the side ratio of 5 over 4 has to be in the same proportion as the 10 is to y, we can call it. And then we get 5y equals 40. So my other dimension is 8 inches. Whoops, wrong side of the rectangle here. And that goes here, 8 inches. So I found my other two dimensions. So the dimensions are 8 inches by 12 inches. So you really have to take a look at what is the information you're given. If you're given the side ratio and you're trying to find areas, then you have to square that side ratio and use that. If you're given the areas, you need to reduce it and then take the square root to get back to the sides. Okay, so now we have another question we'll look at here. This one's maybe a little bit trickier, but we'll try to challenge you a little bit here every so often. A blueprint of the room has the dimensions of 5 inches by 3.5. So we have 5 inches by 3.5 inches. And 0.25 inches, so 0.25 inches on the drawing is equal to 1 foot. So what does that really mean? It means that every 1/4 inch is 1 whole foot. So what that means is that 1 whole inch, there's 4 pieces, four 1/4 inches in 1 whole inch is going to equal 4 times that amount, or 4 feet. So you can kind of process through that, because then what they're asking us to do here is it says, what is the area of the actual room? Well, in order to find that, I'm going to have to find and use this fact that 1 inch on the drawing is equal to 4 feet in real life. So 5 inches would be 5 times 4, or 20 feet. So this is actually 20 feet in real life. And 3.5 times 4 is actually then 14 feet. Oops. There we go, 14 feet. So then, of course, the area, we just multiply 20 times 14, and that gives us 280 square feet. So hopefully this is making some sense here. Again, I encourage you to read the section in the textbook, look through some additional examples. This is the learning target and the homework problems. Again, you can either download the problems right from the textbook into Notability, or just do it on paper and take a picture, whatever you prefer. Try to check the answers. I know that some of you are struggling with finding the answers, so periodically we'll have additional answers that I will post from the actual answer textbook from the teacher's edition. So I'll try to do that as I can find them. All right. Well, have a great day.